The following presentation is recovered from a 2021 PDF draft time capsule for Foundations of Differential Geometric Algebra by Michael Reed, who is me, the author of Grassmann.jl computational language. Welcome to Foundations of Differential Geometric Algebra. Differential geometric algebra is a style of computational language which I've been exploring for several years now. And in this presentation, I'd like to look at some of the mathematical foundations that are involved in this. The computational language which I've been designing for differential geometric algebra over several years is a highly abstract concept which I've been developing in my mind quietly and manifesting in computer programming language using the Julia language and the Wolfram language. When I set out to work on this, the tools I desired based on these foundations didn't exist. So I went ahead and created the kind of foundations I envisioned. Please help sponsor and fund this research and development project. While there are many tricks and special techniques I used specific to the programming languages I implemented this computational language for, this presentation is primarily based on fundamental mathematical principles. So it's going to try to avoid being specific with the programming language. The goal of this presentation are to emphasize some specific foundational aspects which I believe some people have overlooked in the past and thought were uninteresting, while also giving a general overview of differential geometric algebra to a general audience at the same time. I've chosen a particular theme to go along with these foundations that we're studying here, and this theme is what I call differential geometric algebra. So that's what we're studying here. I tend to quietly construct mathematical concepts in my mind, so expressing them vocally like this, in this format, is not natural for me, but I've taken the time to do so anyway. So why is geometric algebra fundamentally important? Well, from the perspective of geometric algebra, we have a unified foundation for the complex number flat geometry, the quaternions with a 3D rotational algebra, linear algebra and bilinear transformation, the exterior forms algebra, and the multilinear determinant, a quantum logic lattice, differential geometry, the conformal geometry and the projections, group representation, and also the combinatoric hypergraph. So we are dealing with the algebraic unification for geometry and mathematical physics. Alright, so that's a mouthful of words. But what is it that actually makes geometric algebra fundamentally important? Well, it provides the generalization to the right-hand rule for higher dimensional orientations. So what do all of these things have in common, really? Well, suppose we choose a two-dimensional submanifold, an area inside of a three-dimensional space, and we look at this space as having an orientation, and we want to have a complement to that space, which also has a direction or orientation as well. We can generalize this concept to not just the cross product in three-dimensional space, but in arbitrary spaces, and there's an algebra for this, and this is geometric algebra. And all of these different concepts here, they involve a generalization of this that's utilized in some way. So the goal here is to combine the algebraic foundations of geometry with differential calculus, and to have a kind of universal computational language that serves as a common foundation for many different mathematical things. Taking a look at this graphic from David Hesteny's paper about geometric algebra and calculus, we can see that geometric algebra has taken many years to be passed down through written material until it's reached its current stage at which David Hestenes was making this graphic. And now we've reached a new age where we're implementing in computational language these concepts of geometric algebra, and it's going to be able to be transmitted in a different way, to be used for research and for learning and education and teaching different things. However, along the way of this historical transmission of information, it wasn't entirely a planned out, coordinated transmission. So there have been some missing pieces of information that didn't get transmitted in all parts of, this network of transmission. And one particular aspect which has gotten lost in a lot of people is the original foundations of the Grassmann algebra before the Clifford algebra. And there's some aspects of that which are important and need to be taken into account. With my Grassmann.jl computational implementation of geometric algebra and the Julian language, my goal was to create a type system from which compiled code could be generated for specific computations based on the geometric algebra type information. This resulted in an abstract tangent vector space type operation at compile time. Additionally, this yields differential geometric algebras on the discrete manifold by unifying them as vector bundles or tangent bundles or other general tensor bundles. This creates a algebraic polymorphism based on a TensorAlgebra abstract type system, which is implemented across several packages, including the DirectSum.jl package, which is the abstract tangent bundle vector space type, and the AbstractTensors.jl TensorAlgebra abstract type interoperability with the vector bundle parameter, and Grassmann.jl, which is the differential geometric algebra on the discrete manifold implementation. And then we have Adapode.jl, which is an adaptive multi-step numerical solver with the Grassmann element assembly on top of it. And as an example, we have FlowGeometry.jl, where we can create geometric boundaries and shapes for numerical computations. So that's some of my background with implementing specific programming language designs for differential geometric algebra, where I spent several years refining and experimenting and trying out different computational language designs. And over this time, I've learned some fundamental universal mathematical principles, which is what I'll try to be focusing on in this presentation. When starting with the foundations with Grassmann algebra, One of the most important definitions we need to be dealing with is the definition of the vector space and linear dependence defined on a submanifold. So the vector space definition, we like to talk about something which we just call V, which is a vector space over a field K. So we'll let V be an abelian group with plus. So we can add vectors, and we have an element 1 in the field such that 1 times the vector space is the vector space using the scalar multiplication over the field. And so that is what helps define us the vector space. We need a symbolic definition for linear dependence. So what we say is this set of elements from a vector space is linearly dependent if this exterior wedge product is equal to 0. So basically, when we have a set of these and we take their exterior product of those, or the wedge product, and if that equals 0, that means it's a linear dependent set. Therefore, the field itself is a vector space or a zero submanifold. It's not a product with another one, so it can't be 0, because a singleton set is linearly independent. Like all the elements of it are linearly independent. Where it gets interesting now is what happens when this is not equal to 0. So here we define a submanifold in n dimensionals. So what we have is, if we have n of these vector space elements and we take their wedge product or exterior product and it's not equal to 0, that means it's a linearly independent set that's isomorphic to a n submanifold. And this itself is a one-dimensional subspace, a basis element of a one-dimensional subspace in a exterior algebra. So what just happened here? What we've done is we've introduced a definition using this wedge or exterior product symbol, and this defines linearly dependent and linearly independent in our vector space formalism. This basic summary of a definition is what Hermann Grassmann used to define linear algebra historically, basically. And this is, if we're going to use the Grassmann algebra foundational approach, this is what we have to think about, basically. Next, we're going to introduce grade projections and direct sums. So just for this slide, let's denote V star as the set V, but excluding the 0 element. Now, since we know what the exterior product and linear independence is, we can define the direct sum construction of linear independent spaces. So suppose we let there be some projections from V to the subspaces Vi, then define the direct sum V1, V2, and up to Vn equal to V if and only if the exterior product exists, basically. If because we have this set excluding the 0 element, and that means that it's linear independent. Now let's define grade projection. On the set lambda V, which is the full exterior product space of the vector space, define grade M projection by taking the restriction to the grade M exterior product space. Note that the dimension of the grade projections is equal to the binomial coefficients. And also, when we combine the grade projection concept with the direct sum construction, we can write a formula expressing that the exterior product space of a vector space is equal to the direct sum of a bunch of graded exterior product vector spaces. And this is what brings us to define the multivector as a direct sum of chains or graded spaces. It's of course worth noting that the total dimension of the exterior product space is 2 to the n, which is true to the binomial coefficient expansion. Now that we've looked at the direct sum structure of the Grassmann exterior algebra, let's have a look at the combinatorics of a specific example. Let v1, v2, and v3 be vertices in three-dimensional space. Then we can form a power set from those elements. And if we form a direct sum over the elements of this power set using the operation, when the exterior product is used, we can see that this is analogous to the power set, which is the exterior algebra decomposition. And when we take a look at this formula in this diagram, we can see that the way we take a direct sum over the exterior algebra spaces is analogous to the power set. Another very similar example is a third order tangent bundle operator composition. So if we have three differential operators instead of three vertices, then we can create a similar tensor product structure based on the power set with differential operator composition as the operation. In order to shorten the notation, the operation symbol is left out. So we can see that done with the vertices and with the differential operators. Now we can see that these are very much similar notations, just with a different symbol used. Well, what's the difference between these tensors, these two lists of tensors? Well, actually, there is a difference between them because the differential operator composition is symmetric, whereas the exterior product operation on the vertices is not. It's antisymmetric. And this is the fundamental difference between these tensors, and this is the fundamental aspect of differential geometric algebra, which unifies the antisymmetric Grassmann algebra with the differential operators, which are symmetric, similar to polynomials. So we've seen here that we have these tensor algebra elements that we can enumerate with our indices, and there's a corresponding structure to the power set elements by which we then adjust by introducing the direct sum and the product operation. But there's still a few details that have been left out here so far, and that is the equivalence classes for the tensor elements. And what sets these apart is that the tensor vertices here, they are actually antisymmetric and have equivalence classes. And so if we swap their indices, they actually switch in orientation, whereas the differential operators are not like that. When you swap the indices, they don't change orientation. Now, this is a very important distinction to be able to make, and this is why Grassmann's algebra foundation is very fundamentally important. But another aspect is that sometimes we just want to have a unified perspective on all these things, and that's where Clifford introduced the geometric product, or what Grassmann would call the central product. And this is where we unify all these tensor product operation under a single product composition. Now, let's take a moment to consider the Z2 graded Grassmann algebras, where we take the exterior algebra and decompose it into two parts, such as the real and the imaginary, or the even and the odd, for example. To really dive into this idea, you can consider the conjugation defined by Shirokov using this combinatorial orientational structure using this formula here. Now, if we apply this formula, then we can see that the group sigma 1 and sigma 2 forms an automorphism group. And we call the particular elements in this group the grade involution, the reverse, and the Clifford conjugate, which is the composition of the involute and the reverse operation. While these formulas appear quite abstract here, they are actually just only talking about how to change the orientation of a graded element when this operation is applied. By taking half the sum and the difference of these operations, we can obtain what's called the real and imaginary component, which are projections which define the Z2 grading. And when we take the real and imaginary part, these projections define a direct sum decomposition, which is a Z2 grading into two parts, which is the even grade and the odd grade. In order to construct the differential geometric algebra implementations and computational language which I've constructed, it's necessary to have a pure type system with a tensor bundle and the submanifold. And this is what I ended up creating, basically. In my particular case, there's a tensor basis which contains indices for vectors, differentials, covectors, and functions. Now, in my particular case, the fact that I have both vectors and covectors is just a choice that I made for the sake of exploring mathematical things. But these things are actually isomorphic to each other, and it's sufficient to just have only one type of these things. But sometimes you want to investigate what happens if you unify and combine vectors and covectors in a more non-standard way. Then then it's interesting to have it set as a bit flip in the tangent tensor bundle type, where you can switch from vector to covector in the definition. And similarly, as with vectors and covectors, there's a duality between the differentials and the functions, which I view quite similarly. And so just for mathematical completeness, I have this entire theoretical construct built into the tensor bundle and submanifold definitions and type system. Now, the following definition of tensor bundle is not intended to be the definition of tensor bundle. This is just an implementation of tensor bundle, which is useful for the implementation of differential geometric algebra in computational language. All right. So in this definition of tensor bundle of a submanifold, what we have is we have a few kind of parameters specifying information about this tensor bundle, which is the rank n. And then we have P, which specifies the null basis from the projective split of the vector space. Now this is just a specialized parameter which is of interest in some particular research with conformal geometric algebra. More generally, G is a bilinear form specified by an oriented metric simplex. And nu is the number of indices parameterizing the tangent manifold, and mu specifies the differentiability order of the tangent bundle. Now, just for standard geometric algebra, we can set some of these to 1, and we can set G to the identity. Then we'll just be dealing with a standard vector space. So all of this extra stuff is just to expand on the vector space as a tensor bundle type definition that's built into the computational language to handle certain information at compile time, basically. And so this is a particular choice related to implementing computational language and trying to unify it with the concept of a tensor bundle and the submanifold abstractly. So to summarize it again in different words is basically we want to have a type system in which we can encode certain information such as what type of vector space we're dealing with, what kind of bilinear form the metric tensor is, and what kind of differential operators we're dealing with in this type of algebraic calculations. And this right here is just a particular example of how I might want to set up this definition in the type system and what information I want to encode. But there are actually different implementations, different instances of tensor bundles and so on. So this is just kind of an abstract layout of a whole family of different types of things that could be set up in different ways. The motivation of this notation is having a compact subspace algebra notation. All subspaces represent an alternative basis with a more compact notation than, for example, matrices. The point isn't that matrices are somehow bad or that we shouldn't use them, but in many instances, instead of writing a matrix that's an identity matrix like that, we would just prefer a scalar value representation instead. And in many cases where we have a vector that's just a 1 and some zeros, we would prefer a symbolic representation of that instead. Or if we have something that behaves like a bivector, which transforms like the quaternions, then from the perspective of differential geometric algebra, we would probably prefer working with the bivector representation using the subspace representation of the exterior algebra basis. And similar thing holds for trivectors and the determinant. And this is just a particular example in 3 dimensions, but this can we can be having these questions in any kind of space. We're about to introduce the geometric product, and with the geometric product, it's beneficial to use this compact notation with the subspace algebra based on the exterior algebra basis. Having it as a representation helps actually with doing the geometric product calculations more easily. In order to define differential geometric algebra, we have to define the geometric product, which is oriented tensor combinatorics based product, which Hermann Grassmann I believe, called the central product, and Clifford called it the geometric product. This definition here is for the purposes of the foundations of differential geometric algebra. So I'm not necessarily trying to say that this is a really great way of teaching the geometric product or anything like that, which there are many resources out there to learn about the geometric product. But what I'm trying to do here is to introduce a definition into the foundations of differential geometric algebra. And the way I like to do this is with this particular definition, which I haven't seen around before. So I like to break up the geometric product into several subcomponents using a tensor product decomposition. And the way that works is I split it into two parts, which is the oriented symmetric difference operator, which is weighted by a bilinear form, and the multi-set sum applied to a multilinear tensor product. So what does this actually mean? Well, if we take a look at this diagram expression, we can see that if we disregard the multi-set sum component of the expression, then we're just only looking at the geometric product aspect of things. And with the geometric product, we're mainly talking about an orientation determined by the parity of indices, and then from the subspaces that are being distributively matched. And then we have the determinant of an intersection metric, basically. And then we have the symmetric difference operator applied to the indices of the TensorAlgebra subspace elements in the product. And this is all based on the anti-symmetric Grassmann algebra principle, or when it's in mixed grade, it's kind of a mixed symmetry type of thing, but fundamentally based on anti-symmetry. Now, when we take a look at the second component, which is the multi-set sum, this is where this is extended beyond just geometric algebra and takes into account other things. And in this particular expression, we use the differential operator, since we're not just encoding vectors, but also differential operators in a tangent bundle representation that we talked about earlier. But as we recall, these behave differently than the vectors, and so these have different tensor properties. But even though these behave separately, we can tack these two onto each other in the geometric product definition and make a generalized differential geometric algebraic product, which is what this is basically. So the definition I've constructed, which I don't think I've really seen out there before, is a hybrid construction of the geometric product with additional things tacked onto it. And this is possible because of the kind of diagrammatic description I made here, where I use a tensor product decomposition to explain how, in a particular case, how two subspaces will collide in the product. And basically, this satisfies the associative and distributive property over addition, and so that's how we apply this on the whole multivector space, basically. And as we can see in the example here, is implemented in the Julia language, for example, in the Grassmann.jl package, when we type two different numbers and take a product using regular multiplication, that's actually the geometric product implemented underneath. And what's happening is described in this diagrammatic expression, but in the computational language interaction, we don't have to see any of that happening because this is all part of the mathematical principles of differential geometric algebra. And so it just does all that behind the scenes in the calculation and gives you the result. Having this type of terminology and definition for differential geometric algebra, we can now just think to ourselves, okay, well, the geometric product is just the symmetric difference operator, which is weighted by a bilinear form and oriented by parity. And for the other tensors, it's a multi-set sum. And when we have a mixed variety of tensors, it just involves a mixture of these things. Also note that the geometric product is the same product that's used in complex number multiplication and quaternion multiplication, and this is just a generalization of that using a particular formalism, and this formalism is differential geometric algebra, which is an extension of geometric algebra combined with differential operators or polynomials and functions. Let's take a look at some geometric product fundamental example calculations. For any typical elements from a grade 1 geometric algebra space, we define the square with the geometric product operation as being equal to the diagonal of a metric tensor. So typically we use the diagonal metric tensor G of the algebra, which is how the vector space's tensor bundle is actually defined in the first place. So in this example, we are using the signature constructor for the tensor bundle space, which uses a plus and minus string to specify the diagonals of the metric tensor. And so in this particular algebra, if we take the exterior algebra space of it and we use the geometric product operation on the elements, then they have the properties matching with the metric tensor. So v1 times v1 is equal to 1, and v2 times v2 is equal to minus 1. At this point, it's quite important to note a fundamental property under the geometric product, which is if we take, for example, two grade 1 elements, vi and vj, and they are orthogonal, then when we interchange the indices under the product, vi times vj equals minus vj times vi for this basis. And then also the geometric product and exterior product are interchangeable in fact as well. And this is due to the anti-symmetric property that's built into the geometric product definition that we saw with the parity definition. And it's important to keep this fundamental fact in mind when simplifying the geometric product in your head, kind of when doing calculations in your head, basically. So let's go over some more examples, this time in a fully positive space first, where we square a bivector this time. And so we have v sub 1, 2, and another v12 multiplied by that. And we can actually break this product up into 4 grade 1 elements, v1 times v2 times v1 times v2. And then we can apply the interchanging antisymmetric operation on the 1 and the 2 in the middle. And that changes the sign of the whole expression. And then we can do the squaring a vector simplification that we did in the first example. And we get -1 times 1, or just -1. Now if we go and change the metric to a plus and a minus once again and carry out the same calculation, this time the calculation stays the same up until the point where we do the squaring a vector substitution. And that's where the result starts to differ, since v2 squared equals -1. And so we have -1 times -1 equals +1. And now we take another look at a more complicated example where we take the sum, basically a multivector, and multiply it by a bivector. And if we simplify this expression, we actually get a vector, v2 minus v3. Let's recall the reverse operation, which we discussed along when we were looking at the Z2 gradings of the exterior algebra. And turns out that the reverse is our main anti-automorphism of products, basically. So if we have, for example, vi times vj, and we apply the reverse operation onto this product, then that reverses these two elements, and we end up with v2 times v1. And if we just take a look at this graphs and this diagrams here, we'll notice these are oriented graphs with nodes that are indices, and the arrows are pointing between the two numbers in the direction, basically, of the orientation of the two numbers of the product. And so v12 is the arrow from 1 going to 2. But when we apply the reverse operation, we end up with v21, and the arrow going from 2 to 1. And a similar thing happens with the other basis elements. Or if we take a look at the more complicated example, v12 times v345, if we apply the reverse to that, we get v54321. And so it really does reverse the indices that we're talking about, and it reverses the orientation of indices. And we are aware that basically the indices represent simplices, and the simplices, they have an orientation, and the reverse operation reverses this orientation. Now let's discuss what are symmetrization and anti-symmetrization projections. So in a more general sense, the symmetrization projection, it's also known as an anti-commutator in different literature sometimes. It's derived from this general sum and product formula that is weighted by the factorial j. And more specifically, the commonly known way this is introduced is with j equal to 2, where we basically take take the product of something like eta times omega plus omega times eta and divide it by 2, which is a simple averaging operation which tells us whether this behaves symmetrically or not, because if it were anti-symmetric, then it turns out that the result of that calculation is 0. So it's a projection operation that checks for symmetrization. And likewise, we can construct the anti-symmetrization projection, which is also known as the commutator in some literature. And this is kind of a similar but opposite construction, which is again weighted by j factorial, and it's the sum and the product, again the same thing. However, what we've now introduced is we're going to apply a permutation. So the permutation sigma is basically has an orientation applied to it in this case, as opposed to keeping it the same. And what this does is, well, if we just check the j equals 2 example again, we have eta times omega minus omega times eta divided by 2 factorial. And so we're averaging over the commutation property. And this is helps with the projection of antisymmetric elements as opposed to symmetric ones. These products satisfy various multivector properties, including the associative and distributive laws for the exterior product, actually. So if you are a bit familiar with geometric algebra already, you can check that for grade 1 elements that this symmetrization and anti-symmetrization corresponds to the interior and the exterior product, which behave, symmetrically and anti-symmetrically. And that's why these projection operations align with those things very nicely. But note that the definition of these, they're not exactly the same. They're not defined in the same way. The construction of the definition we arrived at from these in different ways, which we haven't constructed the interior product yet, but we'll still be constructing it. And the exterior product, the way we defined it, is differently than from this operation which uses the geometric product. So we are now introducing the geometric product and reconstructing the exterior product in some sense or form by using these projection operations. And from this projection thing, we get equivalence classes. And as we saw with the Z2 grading and the direct sum construction earlier and the projection there used there, when we have some kind of projection construction, we can construct a direct sum of the TensorAlgebra space. And what's going on here is we can split up the TensorAlgebra using equivalence classes, and that's what we'll be getting into next. Now we can really investigate what's going on with Grassmann's exterior product operation. So we have, let's consider v sub I wedge v sub j, and it turns out that this equals negative v sub j v sub I. And this is the anti-symmetric property. And we haven't talked about this yet, but this is actually how Grassmann defined the exterior product operation originally. Because if we take a look at what this implies that if j is actually equal to I, then we have v sub I wedged with v sub I, and we have negative v sub I wedged with itself, and the positive and the negative version of that have to equal each other. And the only way that's possible is when it's equal to 0. And so this antisymmetric property actually implies the linear dependence property that we introduced at the beginning of this presentation when we first started introducing the formalism for differential geometric algebra. So this kind of circles back and loops back on itself and goes full circle in a variety of different ways when we go over all this information. So it's difficult to construct a linear timeline when presenting all of this. But what's really essentially important is that we're interested in constructing this antisymmetric property, which we saw previously can be constructed from an antisymmetrization projection operation, which is constructed with a geometric product, which we constructed on top of the exterior algebra space. And now we see that the property that we require for the exterior product in the first place, which is the linear dependence property, that is implied by the antisymmetric property itself. And so this is just all highly fascinating in terms of constructing the foundations of differential geometric algebra. Now that we've discovered this kind of interesting relationship in how the antisymmetric property is related to linear dependence and how the antisymmetrization projection is related to the geometric product, we can create a statement of that, which is this definition proposition type of statement that I've constructed here. So for the exterior product, determinant, and antisymmetrization, for any permutation sigma, the exterior product of the basis vectors can be rearranged using this permutation sigma as a tensor product. And we'll say that this is if and only if the geometric product of those is equal to the antisymmetrization of those. And this yields a tensor modulo antisymmetrization equivalence, because this is the equivalence relation here, and so this results in equivalence classes. And these are associative and distributive over the tensor basis addition. And in a similar way, we can do the same thing with the Leibniz differentials and the derivation and the symmetrization. Because for each permutation sigma, we have the derivations, which have the derivation property, and we know that the differential operators can be interchanged in order, and so they satisfy the symmetrization projection when under the geometric product, which unifies the exterior product and the general tensor product, which includes the differential operators, and it equals that because it's symmetric. And again, we get the equivalence relation, which holds for those tensors and the equivalence classes. Now, the reason why studying a bunch of these equivalence classes and equivalence relations is interesting is because when we use language for cognition, we basically have to rely on using equivalence classes of things to identify properties and be able to transfer our understanding between them. And in the construction of the foundation of differential geometric algebra, what we want is to have some kind of general tensor algebra construction, which is simple to have, and then to apply equivalence classes and equivalence relations on top of that, which refine and the elements that we're talking about and get more specific and have different layers of abstraction when we're talking about it. And what's particularly interesting with this construction that we have here is that it's based on taking a look at the geometric product and the tensor product and the exterior product and the differential operator composition, and unifying these principles in a way that makes sense by having the anti-symmetrization and symmetrization projections constructed in terms of the unifying geometric product, and also relating that then back to the tensor algebra and the exterior algebra basis with the anti-symmetrization and the differential operator basis. And this is all now unified in a nice way, and we can describe it in this foundations of differential geometric algebra in a nice way. So there may be some people who wonder, well, why am I here using these strange symbols to discuss all this, and why am I looking at the foundations of differential geometric algebra from this perspective instead of talking about some kind of geometric intuition or something like that from the beginning? Well, it's because I'm just trying to construct a particular foundation that has certain ideas mesh nicely together with each other, and I'm trying to look at it from a very abstract and conceptual foundational point of view in terms of the mathematical representation. And I'm not necessarily trying to think right now, well, what's the best way of teaching this to people? Because I'm just kind of gathering my thoughts about how do I want to organize these ideas conceptually, abstractly, and then once this abstraction and conception has been made, then one can maybe think about how can it be presented in a teaching, learning type of way. But this is still very much a development in terms of computational language, and it's still moving along in terms of how to construct these foundations. And part of the goal in this construction and these foundations is that I wanted to set things up in such a way that we can have the geometric product and linear dependence and these symmetrization, anti-symmetrization projection introduced already, so that now we could reach this point where we can introduce these equivalence classes and equivalence relations and talk about how they have a relationship with a geometric product. And that's why I made this construction kind of in this way, so that it can lead to these different thoughts about language and equivalence relations, because we use language for cognition, and so we need to make these equivalence class cognitions with our language when we interact with mathematical concepts. And so being able to conceptualize the relationship between these different product operations and how the equivalence classes are constructed from that, I think that's a helpful thing to have. Although that's maybe a very advanced and abstract and weird way of looking at it for a beginner. This is the kind of foundational construction that I'm interested in at the moment. Now, since we've talked about the foundations of differential geometric algebra in terms of linear dependence with the exterior product and the geometric product constructions that we can create from that, we are now going to take a look at one of the heart of the matter of differential geometric algebra, which is the Grassmann's duality and the Hodge complement. And this is where we're going to take a look at some of the definitions and theorems that we're going to cover in this presentation. And I saw that there's a few people out there who somehow don't use exactly the correct definition or something that's incompatible with this. So I wanted to kind of make it clear what the original Grassmann and Hodge definitions were, or at least what they should be in terms of a modern differential geometric algebra foundation, and how they should be, what kind of theorems you can talk about and things like that. So I wanted to be kind of more specific about it. And that's why in this presentation we've built up the foundations and we've created a geometric product and so on, and we're now ready to talk about the original Grassmann's duality and the Hodge complement. So what are we actually talking about here? And so we'll define it. We're talking about the Grassmann-Hodge complement, which is often represented with the star. So let omega be some kind of exterior product, and then we let star omega be the reverse of omega times I. So then it turns out that this star operation takes something from an exterior graded space of P to an n minus P space. And this is called the Grassmann duality and the Hodge complement. So what we're doing here is we're combining several different concepts we've previously covered. We're combining the exterior product, and we're applying the reverse anti-automorphism, and then we're applying the geometric product with the pseudo-scalar in the space. There's this thing called the orthocomplementary propositional lattice in quantum logic, and for that you need something called a join, a meet, and a complement operation, which is analogous to a union, an intersection, and, a complement. And this is associated with something called the De Morgan's law. And what we have is we have these operations, which is the exterior product and the regressive product, which Grassmann originally talked about, and the complement operation, which talks about the duality. These satisfy the property that the complement of the regressive product is equal to the exterior product of the complements. And that is the De Morgan's law, which is analogous to the law that we have in logic and set theory. However, this is where we're going to have to nitpicking our statements about what we're talking about, because this is only completely true for Euclidean or flat algebras in general. So the original Grassmann complement must be used which was before we introduced the metric tensor, which was the Hodge complement. So let's get more precise with our language. When we mean original Grassmann complement, we're talking about this kind of vertical bar notation that is associated with the original Grassmann writings. And in this operation, it's the same as the Hodge star complement, but it is always with the Euclidean flat metric where g equals to 1. And so when we have original Grassmann complement, that's when this De Morgan's law is satisfied. In general, though, we have, because of the geometric product, the introduction of a metric tensor value that's not necessarily equal to 1, depending on the tensor bundle choices that we make. And we can construct the interior contraction using the operation with the regressive product and the complement, the Hodge complement. It turns out that we actually need both of the Hodge complement and the original Grassmann complement in a hybrid fashion if we are to make kind of a really modern foundational construction of these terms. Because when Grassmann was originally talking about this, the theory wasn't as far as it is now, the understanding behind it and the algebraic language that we have, that we can use to talk about things. And because now we understand things better, I can say in retrospect that the interior contraction formulation that we're looking at here, which we're going to get into more in a bit later, but this is just kind of a preview of that, or a side note, that we need both the original Grassmann definition and the Hodge definition simultaneously in the foundational construction. And it's not just some kind of random thing. It's actually both of them are needed, and these are the ones that are needed, the original Grassmann complement and the Hodge complement, and not some other arbitrary choice that you could be making. And by taking a look at some of the theorems and properties that this complement needs to satisfy for differential geometry, for example, we can understand that this is indeed the right choice that we need to make, that this is the Grassmann and the Hodge complement that's needed. And the reason why both of them are needed is because, as I said here, it's this De Morgan's law. It actually only applies with the flat metric when g equals to 1. Otherwise, it doesn't apply. And that's why the definition of the regressive product that's used in the interior contraction is based on the original Grassmann complement operation in the construction of it. And so even though that's the case with the regressive product, it's still the case that the interior contraction uses the Hodge complement in combination with the regressive product that's based on the original Grassmann complement. And so this kind of nuance makes us kind of aware that there's both of these complements, the Hodge complement, which has a metric built into it, and the original Grassmann complement, that both play a fundamental role in the foundations of what we're talking about, or what we're going to talk about with the interior contraction coming up. And in fact, this is something that's fundamentally built into the computer language design that I've been working on. So it's just a part of the reality of working with differential geometric algebra, that there's a Hodge complement, which is the primary definition, and the original Grassmann complement, which is another primary definition that's kind of more specific than the Hodge complement. All right, so we've talked a lot about complements and how there's these two different complements and so on, but that's all a bit abstract because it's just in terms of algebraic expression that we took a look at it and the definition of it. But we could take another look at an example of it in terms of the hypergraph representation. If we view multivectors as hypergraphs, for example, if we have V123, a hyperedge, and we take the complement of that, that is another hyperedge. And when we visualize it in terms of the connectivity of the hyperedges, we can understand that the complement hyperedge is truly takes up the rest of the total space that we have. So if there are 7 vertices, it makes a tetrahedron out of those other 4 vertices because of the ones that were taken up by the 1, 2, and 3 triangle there, that the complement of it has to be a tetrahedron. Now, it's not just the case that we have a complement here, but these have orientations. The triangle has an orientation, and the tetrahedron is a hyperedge that has an orientation, and the complement operation sometimes has a metric tensor that also weights the complement operation in a particular way. And so this is a bit more complicated than just hypergraphs because it has orientation and sometimes the weighting from the metric built into it. Let's take a look at one of the most important theorems or axioms in differential geometric algebra that are out there. So this isn't something that I came up with. This is something that's been discussed in the foundations of Grassmann algebra and differential geometry in various places. But this particular proof that I've constructed here, I haven't seen that before. This is a new way of thinking about this. So in some of the other literature, this is taken as an axiom. For example, an axiom for Grassmann algebra. But in my foundations here, I'm going to look at it differently. I'm going to look at it as a theorem that's derived from the definition of Grassmann and Hodge complement that I've given previously. Because in some of the other foundations, there wasn't such an explicit definition of the Grassmann-Hodge complement as explicit as the one that I have given here. And so as a result of that, because my definition is much more explicit, I can turn things around and I can make the complement of a complement theorem a thing. Instead of having it be an axiom, I can make it a theorem and look at it from that kind of foundational perspective. And so that's what we're doing here, and I don't think I've seen this particular kind of theorem approved before for this in this kind of way. So how does it work? Well, we'll let omega be a grade m element, and we take the complement of this, and that's supposed to be minus 1 to the m times n minus m times omega times the absolute value of I squared. This is a fundamental theorem that's foundational and important. And so it's important to be able to kind of prove this and to verify that the choice of Hodge complement that we've made actually satisfies this theorem. And it does. So we can take a look. So let omega be a grade m element, and then we can rewrite the expressions using the definition I gave previously. And then what we can do is we can take the reverse of omega and extract out the minus 1 to the m times m minus 1 over 2. And because we can extract that out, we have a different expression, and we can once again extract out another minus 1 raised to an algebraic power, and by extracting the reverse operation from the omega times the pseudoscalar. And by doing that, we can now rewrite the pseudoscalar as a square product, and we just have the omega by itself now in the product. And we have a product of minus 1 to some raised to some power. And this expression can be rearranged by using algebraic manipulation of these powers of minus 1. And if we write it in such a way that we have minus 1 times m to the n minus m, and minus 1 times n minus 1 over 2, then that is once again a reverse operation that can be replaced in or rewritten in the expression. And so when we rewrite this expression, what is it? Well, instead of I squared, we have the reverse of I times I, and we have this, and the reason we want this is because we can write this as the absolute value squared. And now we have the result. Actually, that is the result of the theorem, and the result follows because negative 1 to the n times n minus 1 over 2 times I squared is the reverse of I times I, or the inner product of I with itself, or the absolute value squared of the pseudoscalar. So the theorem is proved. And we just did it using the foundations of differential geometric algebra that I've presented here. And I don't think I've seen a proof of this theorem using these kind of foundations anywhere else out there in the literature. So I think this is an interesting new way of looking at it and being certain about the truth of this theorem, instead of talking about it as an axiom and having the complement be some kind of mysterious operation. We've changed it around. In my foundational perspective, I have an exact, explicit definition of the Grassmann-Hodge complement, and the complement of a complement thing is a theorem instead of an axiom. So I think that's an interesting way of looking at it. Let's take a look at foundationally important properties of complements, since we've taken a look at the complement of a complement theorem in its general form. There's a more specific form restricted to just the original Grassmann complement. So when we just restrict ourselves to the Grassmann complement axiom with a flat manifold, let omega be a grade m element of Rn, then the complement of that has to be minus 1 raised to the m times n minus m times omega, since the absolute value of the pseudoscalar squared equals 1. The following lemma and corollary are helpful. Let omega be a grade m element, then the regressive product of the pseudoscalar I and omega equals omega. So the proof of this is fairly simple, actually. If you apply the Grassmann duality principle with the regressive product and the exterior product and rewrite the expression as an exterior product, then we can simplify the expression by observing that the Grassmann complement of the pseudoscalar is just 1, and then that means that we are taking the exterior product of 1 with the Grassmann complement of omega. And because we are now just saying that we want the inverse Grassmann complement of the Grassmann complement of omega, this just means we're just asking about omega. And so the result equals omega, and the lemma follows as a result. Now, another obvious corollary is that the reverse of omega times a pseudoscalar equals the inner product of I times omega, since I times the inner product of I and omega equals the regressive product of I and star omega, or the Hodge complement of omega. And by the lemma that we just observed, we know that this is just equal to the Hodge complement of omega itself, and therefore it equals the reverse of omega times I, the pseudoscalar, and the corollary follows. So it's just kind of an interesting, obvious thing. Once you know all this thing about the Grassmann complement, the Hodge complement, and these theorems, these kind of things kind of just follow as an obvious result that kind of makes sense once you get into these type of results. Now let's take another look at an example of a theorem, which is the interior and exterior product with the Hodge element. And so if we let omega be a grade M element, then the regressive product of omega and the Hodge complement of omega all times the pseudoscalar I is equal to the exterior product of omega and the Hodge complement of omega. This is kind of a fundamental observation that's important and that you find maybe in some way or form in some places. And this is a expression of it in terms of the operations that we're using in the foundations of differential geometric algebra. And we're going to attempt to provide a proof of that here by expressing it in this way. So based on the properties that and the expression rewriting that we've done, we can rewrite the expression in this way such that we end up with a exterior product expression instead of a regressive product. And then we can factor out the metric tensor component from the Hodge complement component in such a way that we can apply the complement of a complement axiom restricted to the original Grassmann complement to the expression, and rewrite the expression in such a way that we have -1 times m to the n minus m. And then we have an exterior product properties that we can apply and rewrite the expression once again, and we can have a simpler exterior product expression as that we can now refactor actually again the metric tensor component that we factored out into the exterior product expression that we have in order to make the Grassmann complement into a Hodge complement, because this extra factor is basically what is the difference between those. And then we just know that we have to multiply this whole expression by I, the pseudoscalar, in order to prove the theorem. And so that's how we can get theorems like this that we can observe using differential geometric algebra when we explore the properties of the elements and the algebraic expressions that we can make. So we've seen that we can construct expressions using the Grassmann and Hodge duality complement and the exterior product and the regressive product, and we can create expressions that are equivalent to each other and make proofs of that. Now, another thing that we can do is we can extend this proposition of writing variants of expressions by making variants of expressions that involve the interior product and the exterior product. So suppose now, what if we want to write the exterior product, not just in terms of a regressive product, but an interior product. And this is what this theorem states, that you can do this, and you can also write an interior product in terms of a regressive product, which can be written in terms of an exterior product. And so this is kind of another variation on extending beyond what we just did in the previous theorem, which goes to show that we can find interesting formulas relating expressions with exterior products, regressive products, interior products, and the Grassmann-Hodge complements. And if we move on to the next theorem, actually, here's another more simple result that we could consider, that if we have eta and omega being grade m elements, then if we take the reverse of those elements, the inner product still equals the other interior product. And that's due to the property of squaring the powers of -1, which just cancels out those, making the expressions equal to them. Having taken a look at some of the variants of expressions involving interior products, we can now take a look at this corollary involving the absolute value of an element omega squared, or the interior product of omega with itself. So if we take that and multiply it times the pseudoscalar, that equals an exterior product expression based on the theorems that we've been taking a look at. We can see that that's a result basically by applying the last two theorems. And then because we've now rewritten the interior product as the exterior product, and we can actually go a bit further and not just rewrite this as an exterior product, but we can make it a geometric product. And rewriting this as a geometric product, we have the Hodge complement still in our expression, but even that can be rewritten as a geometric product. So we rewrite the geometric product once more, and we obtain the reverse of omega times I, the pseudoscalar, and that turns out to be just the absolute value of omega squared times I. And this is basically if and only if we choose basically that the interior product of omega with itself equals the reverse of omega times omega using the geometric product. And this is basically one of the reasons why we have chosen some of the definitions we've chosen in terms of the original Grassmann algebra foundation. Is we want to have this arrive at this corollary, which helps make sure that we're using the correct algebraic properties. It's now time to address a divide in the geometric algebra literature. Specifically, if you've done enough studying about geometric algebra and Grassmann algebra, you will know that there are both a left and a right contraction, which can define the variance of the interior product. Now, in this presentation, I've tried to avoid up until now addressing which one of these I've used, because I want to address it now at this point where we have enough foundations to talk about this. But up until now, I've just been using the right contraction, the original Grassmann right contraction, as the default interior product for what we're talking about. And this is true to what the original Grassmann algebra did and what John Brown was talking about in his exposition about Grassmann algebra. What actually is the difference between the left and the right contraction? Well, if we take a look at the table we have here, this table which I created demonstrates that when we look at the geometric product construction of the left and the right contraction, where it's the reverse of eta times omega using the geometric product, and then using a grade projection using s minus r or r minus s to project onto the grade space. So what was the actual difference there between the left and the right contraction? It was s minus r and r minus s. And due to the way grade projection works, you can't have negative, grades. So the operation actually just is zero when it's negative. And so that is the difference between these two operations, is how the grade projection behaves based on the parameter s minus r or r minus s, which is determined by the grade of the input elements eta and omega, r and s. If we look at the other side of the expressions in the table, we see that we can use a regressive product in the Hodge complement to express the same contraction product instead of using a geometric product with a grade projection. So by just applying the grade projection on the inputs omega and eta, we can restrict ourselves to the S and R grade, and then we can use the regressive product in the Hodge complement in this compositional way, such that it gives us the same result as when we use the geometric product and the grade projection. But what is fundamentally important here, which differentiates some of these expressions, is the role of the reverse anti-automorphism in the expression. So in the geometric product expression, we use a reverse anti-automorphism, whereas in the regressive product expression, we don't require it. This is where I've discovered a multiverse of variants of interior products, which is a rift in the geometric algebra literature. And this table here maps out what I've discovered out in the wild world in the wild west of geometric algebra, where there are different types of expressions out there. And in particular, the way this table works is it's actually quite systematic, and it's fully kind of maps out most of what we would see in terms of variants of these. And the most important one really is just the Grassmann and the conventional variants. Now the Grassmann one is what we've been talking about in this presentation so far. It's just the first row in that table. And now what happens if we just focus on the right-hand side of the expressions? We see how the geometric product is a composition of two elements, eta and omega, and one of them can have an anti-automorphism applied to it, which is the reverse tilde operation, and the other one doesn't. And you can swap around which of the input arguments has the anti-automorphism applied to it, or it could be neither of them or both of them. Now, the Grassmann original definition would involve a single anti-automorphism on the left-hand argument, while the conventional approach has no anti-automorphism in the geometric product expression for the contraction. Instead of using the geometric product expression on the right-hand side of the formula, we can also take a look at the regressive product expression and how the anti-automorphism is applied to the input arguments and how they compare across the table. And similarly, we can find that there's a pattern which is similar but not exactly the same pattern as with the geometric product expressions. All right, so why would I bother tabulating this multiverse of possible expressions for the interior product contraction, which has a left and a right variant and a Grassmann variant and a conventional variant? Well, the reason why this is tabulated here is because as I was reading the geometric algebra literature and differential geometry literature and trying to unify these things in my mind and build a foundational structure that is consistent across all these different things, I realized that some of the literature was using the conventional definitions when referring to things, as opposed to the original Grassmann definitions, which are used in a lot of differential geometry and the original Grassmann definitions. And so some of the newer modern geometric algebra literature, unfortunately, somehow diverges and uses the conventional expressions instead by default and implicitly in certain ways and expressions. And so it's important to understand this fundamental distinction that in some ways the expressions, the result of them, they'll overlap with each other and be the same in a lot of cases, and there'll just be some special cases where the results differ due to how the anti-automorphism application affects the definition. So the important thing which this table tries to emphasize when I created it was that some of the different literature out there will stick to some particular convention implicitly in their definitions, and which are different from the original Grassmann implicit conventions. And so I would like to be able to map that out and understand and differentiate that and be rigorous about the mathematical origins and meanings of these expressions and disambiguate the context of the language in these different contexts. Does this present any practical problems? Well, as if we just stick to the multiverse of the variance of interior products the way it is in this table here, it's not all too bad because each of these expressions can be obtained from another one by applying some anti-automorphism to the input arguments of these expressions. And so it can all be recovered and we can translate between these things, and it's not that difficult once you're aware of this, just to kind of keep track at the back of your head, whether you need to apply some anti-automorphism when you're understanding different literature out there in terms of what variant of interior product is implicitly assumed in the definitions. Now, there is a particular reason why in the foundations of differential geometric algebra, as I have laid them out and constructed them so far, why I've chosen to use the original Grassmann convention and definitions in my work. It's because there are theorems and definitions which are found in some of the differential geometry literature, and especially in the Hodge and theorem things that have been written that are based on that. They will use some theorems and definitions which are compatible with the original Grassmann algebra, and some of the other geometric algebra literature, it has some slightly different implicit assumptions about how the anti-automorphisms are applied to the interior product contraction variance, then that is something to be aware of, and it could make some of the results incompatible by having a plus or minus sign end up in an expression being equal in such a way that it makes all of the mathematics inconsistent. So that is something you might have to worry about and be aware of. And that is one of the problems and issues I'm trying to address by having awareness of it with this table. But why is it important for me to have awareness about this issue with this table? Well, if we take it one step further and we consider that in some people's work they use a complement operation, which is not exactly equal or the same as the original Grassmann complement operation or the Hodge complement as we discuss it here in this presentation and this foundations of differential geometric algebra. And so if you start changing that and you start changing, the convention that you're using for left and right contraction, whether it's the Grassmann one or the conventional one, then that introduces potential errors and variabilities in expressions and results and theorems, that now it's no longer possible to say that some expression that person wrote in this when they made these other assumptions, that's at all compatible with the differential geometry literature or the original Grassmann algebra theorems that we're interested in. And so that's why in these foundations of differential geometric algebra, which I'm talking about here in this presentation, and which I've built and implemented in computational language with my Grassmann.jl package, and also into the Julia language and also the Wolfram language. The goal with all that is to have a foundation that's built on the correct, rigorous way of thinking in terms of the original Grassmann algebra, and having the awareness about different conventions and using formulas that satisfy the original theorems of the original Grassmann algebra. Because, I've tested some of the other computer programs that other people have made, and when I check whether the Grassmann laws are satisfied with the complement operations and the regressive product and the exterior product, and trying out different ones of these theorems and expressions that should be satisfied, I find that it's not satisfied. And some of these computer programs that other people have written that claim to be about geometric algebra, they don't satisfy the Grassmann laws or some of the theorems that we've discussed here. And so that's why these foundations I'm building, that's why, some people may have thought this is a boring presentation because it's just a bunch of math and some weird theorems and symbolic notation. But I'm actually trying to address some of the foundational questions and issues. And by building a foundation for differential geometric algebra and the way I have, then we can better understand what's going on in the geometric algebra literature. And if you do encounter some kind of weird discrepancies or errors or inconsistencies in the mathematics, it might be because you use some of these other people's literature where it somewhat diverged from the original Grassmann implicit understanding to a different implicit understanding. So as I've stated several times now, the goal here is to consider the foundations of differential geometric algebra. And the reason why we want to try to get this correct is because we want to be able to use some of the theorems from Grassmann algebra and use them with differential geometry and combine them with geometric algebra. And we don't want to have some kind of inconsistent issues, because when you have an inconsistency, that can lead to just garbage mathematics. Like you might just have to throw some of that in the garbage if it's inconsistent. But just because there might be some issues like that, it doesn't necessarily there are, but there could be some that that I've encountered, for example, when I check some other computer programs. But when you're reading some of the literature, what you can do is you can try to get the gist of what it is the author is trying to get at, because there is something that they're trying to say, and recast it in terms of the foundations of differential geometric algebra, as I've been talking about here. Because that's what I do, at least for myself, is I try to recast the information that I'm receiving about from different sources about the mathematics of differential geometry and geometric algebra, and I try to make sense of it in terms of the theorems and definitions and foundations of differential geometric algebra as I've laid them out here. That's why I'm doing all this, and I decided I'll record this presentation so that other people can have some thoughts about this as well. Consider the situation where someone is selling a cheat sheet that has all this kind of information about formulas and tables of geometric algebra expressions. And suppose this is based on some computer program and some understanding someone has built up based around using some kind of complement definition that isn't quite equal to the original Grassmann or Hodge complement, or they've made some other choice about the convention in the variance of the interior product. It could be then that these tables and cheat sheets that you purchase, that they're going to be inconsistent with some sort of differential geometry literature that assumes that you have some kind of consistent theorems that satisfy the original Grassmann algebra theorems and axioms. So that's why this is something I like to investigate and think about and be aware about in my own research, at least. And unfortunately, there's going to be some people in teaching this who are going to want to create teaching material, but they're not nuanced enough with their definitions and foundations and implementation of what they're doing and talking about, that they don't satisfy the original Grassmann algebra theorems and axioms anymore. And so that's something that can happen with the ongoing development in history. As people try to spread more information, there's going to be some people who try to teach this material, but they weren't rigorous enough in their definitions. And there have been some people who I brought to their attention some details about the variance of the interior products and how the Hodge complement should be defined, and testing out certain expressions that should be satisfied due to the theorems based on the original Grassmann algebra. And they don't satisfy them, and I show the example, and they just don't want to be that rigorous about it when I confront them about it. And they just want to keep doing it their way because they think it's some kind of choice that you can make that makes sense for them from their perspective for whatever reason. Unfortunately, the issue is that if there is some kind of inconsistency that gets introduced with some of the other literature that makes assumptions based on the original Grassmann algebra, which a lot of the differential geometry literature is based on that. For example, the Hodge and theorem literature and the writings based on that, they're going to require a nuanced understanding of some of the definitions, and you you have to be rigorous, and unfortunately some of the people teaching this material, selling you cheat sheets and so on, those are not nuanced enough to really take into account all these things. And that's why when putting together the foundations of differential geometric algebra, I'm trying to address some of these things, and that's what this presentation is focused about. There's other presentations you can go to get more of an intuition about certain geometrical insights and things like that. Here, I'm mainly talking about the foundations of differential geometric algebra and what to be aware of. Computational language that's consistent, has the right kind of mathematical properties and theorems that satisfied. We've now reached a point in the presentation where we can gradually stop climbing uphill, and we can reach a sort of plateau at the Grassmann-Leibniz mixed tensor algebra kind of review slash overview, where we kind of have now covered enough of the foundations that we can talk at a more higher level about differential geometric algebra in the way that we'd like to see. So two of the particularly interesting operations that we're going to get interested in are the so-called boundary operation and the exterior differential. And what's interesting about the boundary operation is that it satisfies what's called the Poincaré lemma. And that means basically if you compose the boundary operation with itself, that equals 0. This is just a fundamental property that you can check based on, the properties of exterior algebra and the regressive products and the complements and so on. But how is this actually defined? Well, the boundary operation is basically we start to introduce the differential operation nabla, which is a sum of differential operators multiplied by the vector basis. And that's a mixed tensor now. We're now no longer just talking about the vector basis. We're talking about a mixed basis with differential operators and vectors combined. And that's why we have in differential geometric algebra in our foundations so far, we have considered both kind of tensors as part of our tensor algebra and part of the operations in our algebra. We can deal with both the vectors and the differential operators. And now we take the epsilon, for example, and take the regressive product with the complement of this nabla, basically. And that defines the boundary operation, which when composed with itself is equal to 0. And there's a similar thing that's called the exterior differential, and that's D. And that's formed by basically taking the nabla operator and wedging it, or taking the exterior product with the form omega. And that is similar to the curl and the cross product if you also apply the complement operation additionally in composition with the external differential D. So the more abstracted notation of the external differential and the boundary operator, they somewhat hide the fact that what we're doing is we're combining differential operators with the exterior product and with the regressive product, both by applying the Hodge complement to the expressions. And if we more explicitly write it out, then we can see what the definition is saying. But it's quite nice to have this compact notation offered up by the boundary operator and the exterior differential. It should also now be trivial for you to check that d applied twice, or dd, should also equal to 0 in a similar Poincaré lemma fashion as the boundary operator. And that's trivial to understand if you recall from the beginning of our presentation the property of linear dependence. It's a simple application of that property to see that d applied twice is also equal to 0. Now we'll get to one of the most important theorems of differential geometric algebra, which is the so-called Clifford-Dirac-Hodge Laplacian decomposition. So what we have is we have this thing that's in the literature called the Dirac operator. But if we study it carefully and understand what it is at its core, and we study the differential geometric algebra foundations, then we can understand that the Dirac operator is nothing but the square root of the Laplacian, which, is a very great mystery if you do not know differential geometric algebra. But if you do know differential geometric algebra, it's not such a great mystery after all, because we can actually understand quite concretely what it is. And it's just the product of nabla and omega. And that's just the geometric product. And in particular, in this theorem, it's not just the geometric product. We have the decomposition of it into the sum of the boundary operator and the exterior differential. So it turns out that taking the sum of the boundary operator and the exterior differential is equal to this geometric product, which is a Dirac operator, which is the square root of the Laplacian, so to speak. But now, once you're aware of this Dirac operator, you can also check that the product that's in the theorem here is actually not commutative. And so if you swap nabla and omega, these are not equal to each other, the products. And however, with the Laplacian, that wasn't the case. Those were equal to each other. It didn't matter whether you applied the Laplacian before or after, and that's because the Laplacian is a scalar quantity, whereas the Dirac operator is not. But we can observe that the composition of the operators can be done in several different ways and understood in different kind of expressional forms. Another theorem which is particularly interesting is the integration by parts theorem that can be fully generalized in terms of the Grassmann-Leibniz mixed tensor algebra. So in this situation, we let nabla be part of the Leibnizian vector field operator, and then we again use d and the boundary operator, and these turn out to be Hilbert adjoint Hodge-Durham operators, which as a result satisfy these properties, and that's what this theorem says basically. So there's actually two parts to this theorem. I've kind of taken two parts to it and combined it into one. And there's this integral theorem with the integral over m of d omega times the wedge product of the complement of eta, and then plus the integral over m of omega wedge the complement of the boundary of eta, and that equals to 0. And another similar expression, it's not exactly the same expression, but it's a similar type of expression, meaning with a similar foundation, and that's when you basically take the inner product of d omega and eta, and omega and the boundary of eta. and we can equate these two expressions to each other as a scalar product expression. And this is a particularly interesting theorem to just think about, and because it's a quite general statement. And this is also part of the reason why we set up all these foundations of differential geometric algebra, because we want to be able to reach a stage where we can talk about theorems like this, and we can be fairly certain about the foundations that we're satisfying the original Grassmann definitions and theorems and axioms that make the theorems that we want compatible and consistent with each other. Let's take a look at specific examples of the exterior differential and the boundary Poincaré duality by taking a look at the vorticity curl of a vector field. So that was by using the complement of D and applying it to dx1, dx2, and dx3. And if we apply this operator, we basically get the vorticity, the curl of the vector field, and that's what the result of that expression is right there. And so we're just going to explicitly take a look at the result of that just to gain some intuition. And in a similar way, we can take the boundary of a 3-simplex, which is these faces. If we take the boundary of v1, 2, 3, 4, that equals this sum, this particular result, which has a bunch of 2 simplices in it as a sum, and differential operators and orientations and so on. And similar to the vorticity curl of the vector field, this is a particular operation in differential geometric algebra, which combines the geometric algebra operations with the Grassmann exterior algebra basis and the differential operator TensorAlgebra basis. Another interesting form of expression that we can start playing around with is when we combine the boundary operator with the grade projection operator and make expressions that way. For example, if the rank of the grade P boundary incidence operator is written in this expression by taking the minimum of these 2 dimensions of these operators by doing this calculation and just calculating the dimension of the vector space that results from the calculation. And if some of the coefficients are 0, that changes the rank of the result, and that's where this kind of information leads to invariant topological information that can be computed using the rank of homology groups for Euler characteristics, which is written chi. And this is the sum of a bunch of these numbers, which are called Betti numbers or Betti coefficients. And we can explicitly compute and play around with some of these in a similar fashion as the rank of the grade B boundary incidence operator. We apply that over and over again several times in such a way that's related to the Hodge decomposition. And by taking the sum of the series of coefficients, we get the Euler characteristic. So this is something that's might be interesting to a bunch of topologists who are interested in the homology and cohomology groups and invariant topological information in differential geometric algebra. Let's take a moment to think about how we simplify Maxwell's equations into a single wave equation. So We can just start by taking the definition of a Faraday bivector dA with dDA equal to 0. So as we know, if we have something like dA, dDA has to equal to 0 just from linear dependence, just because of what we know about exterior algebra and the Grassmann foundations. And we define the Faraday bivector dA as E times Vt plus the complement of B times Vt, where E is the electric field and B is the magnetic field and A is the vector potential. And that's just a definition of the Faraday bivector. Now, we want to think about Maxwell's equations, and they should be transformed into a single wave equation, right? That's one of the goals of, or one of the things advertised about geometric algebra or differential geometric algebra. And since we already know dDA is equal to 0 just by definition, by the definitions of what we already have talked about in the foundations of differential geometric algebra, Gauss's law and Faraday's law are already a given just from the definition of the Faraday bivector. So we don't need to do any additional work when we recognize that Gauss's law and Faraday's law correspond to dDA is equal to 0. But we do need some additional thinking when it comes to star D star dA is equal to J. And this is what we really mean when we talk about simplifying Maxwell's equation to a single equation, because what we end up creating or talking about is the Laplacian of A equal to J, which is the Maxwell's equations written as a wave equation in terms of geometric algebra. And when we really think about this, is star D star dA, or the geometric product of nabla times dA, as I show in the expressions. And these two correspond to Gauss's law and Ampere's law. These star D star dA equal to J. And as a result, that's how we get Maxwell's equations rewritten as a single equation, because we know that dDA is equal to 0, so we don't need to define that equation or really talk about it, because it's kind of by definition and by the properties of everything that's going on in differential geometric algebra. But the equation that we do need to worry about is star D star dA equal to J, and that's simplifying Maxwell's equation into a single equation. We'll take a sort of intermission here to discuss a topic about the conformal geometric algebra light cone and how we might customize our geometric algebra language for the projective split from conformal geometric algebra, basically. And originally I mentioned that the tensor bundle has the option to specify projective split. And this is basically where that custom option comes in. And so what's typically done is we combine the positive and negative metric to create null vectors. And we construct the projective split by adding these two positive and negative metric basis elements in this way. Basically, the plus and minus element, they square to plus and minus 1 because of the metric being plus and minus. And this is a basis where we define v sub infinity to equal v sub plus plus v sub minus, and v sub empty set is equal to v minus minus v plus divided by 2. And the choice to have that divided by 2 is particularly related to the interior product. And first of all, these are called null vectors, v sub infinity and v sub empty set. And this is because their measure is 0. So if we square them, they equal to 0. But if we take the interior product between the two, that equals 1. And the reason for that has to do with dividing the other one by 2. Somewhere we have to introduce another factor. We could have used the square root of 2 and split it up differently, but it is fairly common and conventional, and it makes sense in a lot of ways to divide the other one by 2 and leave the other one as is. And so we take the square of the bivector as well into consideration, which equals 1. And this Minkowski plane, which is a bivector, it products with a null basis in a bit different way than you might expect if you are already familiar with geometric algebra and it's intuitive for you. Then you might be surprised that there are yet some unintuitive things still. And so this is something that might be one of those unintuitive things if you are already familiar with the geometric algebra but not conformal geometric algebra. And so if we take the bivector and multiply it by v sub infinity, it equals minus v sub infinity. Whereas if we take the bivector and multiply it by v sub empty set, it equals v sub empty set. Now, if we take the actual geometric product, v sub infinity times v sub empty set, that equals minus 1 plus the bivector. Whereas if we swap it around and we take v sub empty set times v sub infinity, it equals minus 1 minus the bivector. And this is quite surprising and behaves much differently than one typically would expect in geometric algebra. And this has led to some discussions online where people have said, well, when you have a bivector, that's just equal to a geometric product. And that's actually not the case. A bivector is written in terms of the exterior algebra basis, the Grassmann algebra basis. That's the representation we're using to write a bivector. It's using exterior algebra, linear dependence, those concepts, they construct it. And so when we have a bivector like v, like we have in here with the infinity in the empty set, this bivector behaves much differently than we typically expect, because if we take the geometric product of the two basis elements that we're using here, v sub infinity and v sub empty sets, which are basis vectors, and we take the geometric product of those, that is not equal to the exterior product of them. It's equal to minus 1 plus the bivector, or minus, depending on which order the multiplication was done in. And that's kind of what we're getting at is here with conformal geometric algebra, the algebra can behave a bit differently, and that's why it's specified in the tensor bundle, and that's why there's a special algebra implementation for it at compile time. But this is something that some researchers find interesting to use in their research, and so it's been implemented, and it's part of the foundations of differential geometric algebra. And as has been discussed by David Hestenes also in his papers. As another example, we'll just briefly mention that the conformal geometric algebra has a null Laplacian. And so if we take the 5-dimensional conformal geometric algebra and we take a look at what the Laplacian would look like in this case, Well, this is what we end up with. It's like the typical three-dimensional Laplacian minus 2 times this Minkowski plane differential operator dimension. So that's a quite interesting formula to take a look at and think about for people interested in conformal geometric algebra. Here I'd like to share one of my favorite proofs in differential geometric algebra, which is the Dirac operator decomposition reveals rotoreflections. And this can be broken down into two separate parts, and the first part is the one that's particularly interesting for me. And this is the theorem where the first grade sandwich product is a reflection. And so when we have a reflection by a hyperplane, such as the complement of nabla, that has the isometry omega O slash nabla, which is, this symbol combination is defined as negative nabla backslash omega times nabla. And what the backslash just means is that there's a division going on, but it's on the left side of the expression. So we're inverting nabla and then doing the geometric product to multiply them together. But since it's on the left side of the expression, the division has to be a backslash, and that's why it's written like that. And in order to, simplify all that notation to avoid having to remember all that, that's why omega O slash nabla is supposed to be like a simpler notation, which means we have omega and we have nabla, and we do an operation called O slash on them, and that's supposed to be a reflection basically. And that's a theorem, that it's a reflection and that this is isometry. And the way I can prove this is basically we let nabla be grade 1 element, then omega equals nabla, divided by nabla times omega. That's just kind of multiplying by 1. But we've introduced more symbols, and we can apply the associative property and reparenthesize the expression. And when we start doing things like that, we end up with a different expression, and we can now have nabla backslash d omega plus boundary of omega. And if you recall from our previous theorems, that's an application of the Dirac operator and the decomposition of that, which was d omega plus boundary omega, which is also a geometric product of nabla times omega. And due to the way we have now restructured the way we write omega by introducing this expression, which was initially just multiplying by 1, we have now expanded it out and written it in a completely different way. And what's particularly interesting about this new construction is that nabla is parallel to the boundary of omega, and nabla is also perpendicular to d omega. And if we understand that, we can do the reflection, and we can understand that we reflect by flipping the component that's perpendicular. And so we reflect across the hyperplane, which is the complement of nabla. So let's do that. So we want to prove this by doing the reflection and then getting the expression back that we want to prove, basically. So what we want to prove is that this expression up there is a reflection by hyperplane from the element omega using this hyperplane that's the complement of nabla, basically. So we take the expression of omega that we had, and we apply the reflection, and we now have a different expression, which is nabla backslash d omega minus boundary of omega. And now we multiply this expression by 1 again. We do the same trick all over again that we just did before. And we rearrange things with the associative property, and by rearranging things a bit with knowledge of the geometric product. And by applying knowledge of the Dirac operator, once again, d omega plus boundary omega, we can replace that with the product of omega and a nabla. And since that right there was a nabla squared, which we got from rearranging the product before, we now end up with minus nabla backslash omega times nabla. And that's the expression for reflection by a hyperplane. So we can kind of have an algebraic proof that the reflection by a hyperplane complement of nabla has this isometry omega o slash nabla, where omega o slash nabla is the minus nabla backslash omega times nabla. Why does this matter, and why go through this weird proof that shows that reflection by a hyperplane can be expressed in terms of this formula? Well, this is the same formula which generalizes, and using that formula we can express the Cartan-Dieudonné rotoreflection decomposition, which is a theorem which has been, discussed in the literature of geometric algebra and in other various places before. So if we have this foundation of differential geometric algebra, which we've been talking about, and we take this theorem, which I just showed you and proved for the reflection by a hyperplane, which results in the grade 1 sandwich product formula, that can be composed in several layers so that every isometry from the vector space V to itself is the composite of at most k reflections. And so that's what the Cartan-Dieudonné reflection theorem says. And the way we can express it in terms of a formula is using this O slash notation, where omega O slash nabla 1 and then composed with O slash nabla 2 and so on up to nabla k is equal to omega O slash of the geometric product of nabla 1 times nabla 2 up to nabla k. And so what this helps us understand is that we can express the decomposition of every isometry into a composite of at most k reflections by observing the formula for reflection and nesting it several times. And that's why the theorem which I proved above was particularly interesting. And I don't think I've seen a proof of this theorem before. This is my original kind of insight about how you can prove that a reflection by a hyperplane has a isometry, and this uses the Clifford-Dirac product decomposition d omega plus boundary omega as kind of a application. And that's why I thought this was an interesting theorem to take a look at, because when you apply that repeatedly, that's the Cartan-Dieudonné rotoreflection decomposition theorem when you express it in that way. And you can think about that, check that for yourself. Now that we've taken a look at the sandwich product and the O/ operation and the reflection decomposition, let's consider the differential equation partial I epsilon j equal to epsilon j O/omega. Now the solution to this equation is epsilon j of x equals epsilon j of 0 O/e to the xi omega. And this is the exponential map with the Lie group parameter, and where theta equals 2xi if we do that substitution. Then for normalized omega, we can have these three special cases. If omega squares to 1, it behaves similar to a hyperbolic cosine and sine, whereas if it squares to -1, it behaves like a cosine and sine, like a complex number. And if it squares to 0, it behaves like 1 plus theta omega. This is obtained from the exponential series expansion, which is just as similar as you would expect from studying complex analysis, for example, but a bit generalized. If you study these special cases enough, you'll note, for example, that nabla O/e to the theta omega over 2 equals nabla times e to the theta omega, and that this is like a double covering when we're in R2. Observe how the sandwich product operator requires you to apply this exponential twice, and therefore we only use half of the angle, and in the O/ definition. And so in this expression, that's why in one side it's theta omega, and on the other it's theta omega over 2. It's because of the sandwich product and how that works. And that's what we mean by double covering for R2. Because in R2, this expression is true. So when I hear people talk about there being some kind of mystery in the universe about why there's some kind of a double covering or something like that, I don't quite understand necessarily where that mystery is coming from, because in geometric algebra and the foundations of differential geometric algebra, this is just found as part of this sandwich product definition when you apply it in this way, and it's part of this reflection theorem. And so the rotational properties of the exponential function have to then take into account this particular situation. And it turns out that in R2, you can replace this with a geometric product like the one we have in this formulaic expression. And this is one of the interesting things about R2 is we can now write the exponential that's not requiring the sandwich product. It can be rewritten in this way. And that's why complex numbers are so nice, because it happens to simplify that way in R2. But that's just a special case, and that's this double covering for R2, where it overlaps very nicely like this, and this formula can be applied. It can be rewritten in a simpler way, but that's not always the case. In general, we need this more general formula involving the sandwich product, and it doesn't always simplify this nicely. And so these nice special cases, these are just, particular special cases, but the generality of the geometric product allows us to generalize much beyond these specific cases. Here I'll just briefly add a note about a convention that I have, which is that the sandwich product must have its reversion on the left side. Otherwise, the rotation is clockwise and opposite of the Euler formula phase parameter convention. Now, an example that you can think about when looking at this is, let's look at e to the pi over 4 times a bivector times v1 times the reverse of e to the pi over 4 bivector. In this case, the reverse is on the right side, and it turns out that this is equal to minus v1 with the o slash e to the pi over 4 bivector. And the reason for that is because in the o slash convention, in the sandwich formula and the theorem that we previously proved about reflections, we had a particular way the formula was constructed. And if you and the way that was with this backslash, and that had the inverse operation, which is the reverse operation in disguise, and that's why it's on the left side, because this is on the left hand side of things in that formula, and that's how that formula was proved. And it turns out that that's consistent with the mathematical conventions that we're used to. So if you now suddenly do some kind of other weird convention where you do the sandwich product but you reverse it on the right hand side, then that's actually the reverse, of the convention. It's opposite of the Euler formula phase parameter convention. And that's why I'm just briefly adding this note that if you want to stay consistent with, most of the traditional mathematics, which, like the phase parameter convention of the Euler formula, which is, I think, considered standard, then you might want to use the convention which I'm using, which is that the reversion must be on the left side of the sandwich product, or the way I've used it is we've built it using the reverse in disguise with the inverse, using this little trick in the proof there. But another example we can take a look at in Julia with Grassmann.jl and using these bivectors is, it's this same example that I just explained, but just executed using a numerical computation with a bivector, multivector, to calculate and show how these are opposite conventions, and the result switches sign. Let's take a look at the exponentiated product examples by taking a look at the vector fields. If you are familiar with complex numbers, then you may already be familiar with the rotation around the complex plane that the imaginary unit has when used with the exponential function. However, with geometric algebra, we can generalize this behavior of this bivector. And in the different examples here, we can see that we can have the radial vector field and the swirl vector field, which is halfway between the circular and the radial one. And then when we introduce a reflection into the operation, then we get another type of vector field. And this was all for R2 with basically the imaginary unit. And in another two-dimensional bivector, but using the Minkowski plane, or so-called, or the combination of the positive and the negative metric, then the vector field can take on different forms like this as well when composed with reflections. However, with geometric algebra, we need not restrict ourselves to just two-dimensional submanifolds. We can also investigate higher dimensional submanifolds and vector fields generated from those. And in some of these examples here, we are looking at the four-dimensional submanifold and the projection into 3 dimensions. And there's different ways that you can take a 4-dimensional space and project into 3 dimensions. And there's something that can be used, which is the generalization of the Riemann sphere to 4 dimensions. And that is basically what I used in some of these examples, using the exponential function and this bivector sum. Then these are some of the vector fields that I obtained. An explicit calculation using the exponential function. These particular examples are all available on my GitHub repository, Grassmann.jl. By defining the function in the Julia language using the Grassmann package, which I programmed, you can plot this by doing calculations with them and then translating the result into the graphics framework for plotting. To show some other types of examples, we can modulate the parameters. Instead of plotting a vector field, plotting a single orbit of a modulated parameter, resulting in explicitly calculated paths. These are functions which are explicitly parameterized by t, so they can be calculated at any point in time t by just plugging that in and explicitly calculating it at that point, because it's just the exponential function again. When we consider an eccentric geometric product with an elliptic algebra, then when the geometric product equals -2 in this example, then that means that we must normalize these elements by the square root of 2 if we are to keep up the dilation in the way we expect. And that's because the numbers start growing faster on one axis, so due to the spatial dilation, the exponential theta parameter is also dilated by an eccentricity factor. That's why in this expression we have an extra factor, the eccentricity factor of square root of 2 built into the expression. As this elliptic clock is by a factor of the square root of 2 than a standard circular clock. The radius of the Earth along the equator is r sub e, which is 6378137 meters. But the Earth is not a perfect sphere. It is better approximated by an ellipse with a flattening parameter f, and this eccentricity factor 1.0067395, which is approximately equal to 1 over 1 minus f squared, where f is approximately 1 over 298. So if you understand in advance that this is the eccentricity factor we desire, then using the metric, the radius along the north can be computed with a very small error of 1.6 times 10 to the minus 7%. And using this expression, for example, which results in 6356752.3 meters. It's an example that demonstrates with the result how it is feasible to do nuanced calculation with the Earth's elliptical geoid approximation using a geometric algebra V vector exponentiation. Now, consider taking the points v1, v2, v3 given as a basis for the three-dimensional space, and we construct 3 points to make a triangle in that space. Then P0, 1, 2 is the trivector P0, wedge P1, wedge P2, which is a pseudoscalar in that three-dimensional space. However, another representation to deal with this data structure is to take P0 as a coefficient to V1 and P1 as coefficients to V2 and so on. And this construction is a nested construction where we take vectors as coefficients of vectors. And this is what's called a dyadic tensor. And the way we calculate the volume of the triangle or any simplex, this can generalize to any number of vertices. We just pick any base point and subtract it to get the vector frame. And those points, those frames, you just take the exterior product of them to get the hyperplane. And then the volume equivalence class is just any one of these hyperplanes. You take the complement and then take the norm of that. Then that gives you the volume equivalence class from any base point. So it doesn't matter which base point you pick. If you do this technique of calculating the vector frame by subtracting the base point and taking the hyperplane that results from that, then and then taking the complement and taking the norm of it, that's taking the volume of the simplex, and in this case it's the area of the triangle. So there's 3 different things here. We can take an exterior product of the points that make up the vertices, or we can construct a dyadic tensor, or we can take another exterior product, but this is a different one. This is the construction when we subtract the base point to get a vector frame, and then the resulting hyperplane that we get from taking the exterior product of the construction, that's then the exterior product that we construct. So it's a slightly different product. And that's what really makes the volume equivalence classes of the simplex. Because a simplex with 3 vertices is a 2 simplex. It's a triangle. So what does a triangle have? It has an area. An area is a 2-dimensional subspace, and it's a bivector. That's why this vector frame hyperplane product is a bivector that we get here. It's not the trivector that we get by taking the product of the 3 points, but it's the product we get by subtracting the base point and then taking the area of the resulting vector frame. And a similar concept generalizes to higher dimensional Grassmann elements and any simplex. So this is just something I wanted to cover because there might be some confusion that can arise around how you can calculate the volume of a simplex. Working with simplices is quite natural with geometric algebra and differential geometry. However, what happens when we want to extend that and we want to work with many more points than the number of dimensions they are embedded in. And this is what happens when we want to generalize beyond just the simplex of the space and to take a look at sub-simplices or submanifolds, and to take a look at the mesh bundles and based on Grassmann elements. And here we have icosahedron, which has 12 points that it's generated from. You can, for example, take a cyclic permutation of 0, plus or minus 1, and plus or minus phi, and construct 12 points from that. And when you take the convex hull of that and take the boundary of that, that gives you a bunch of triangles that make up this shape. That's icosahedron. Now we are once again dealing with some triangle facets, which are simplices embedded in three-dimensional space. These are triangles, so they're planar surfaces that are embedded in a three-dimensional space, and we can apply the principle that we saw on the previous slide about calculating the volume of a simplex. In this case, it's an area, it's a bivector that we can calculate. That's the area of each of these triangles, which is composed of 3 points. When dealing with a simplex hat gradient, we are dealing with a Grassmann hypervolumes. And this is a linear algebra problem that people study in the past using the matrix algebra. And here we take a look at it from the perspective of Grassmann algebra and determinants. Well, it's not just the determinant, because in Grassmann algebra we generalize to just exterior algebra. So how does it work? Well, the solution x is substituted into this equation, and it's the sum of a bunch of exterior products divided by the volume of the d-adic tensor. This means that using only exterior products, we can efficiently solve the linear system by allocating a series of products. And it turns out that if you just want to only check whether a point is actually contained inside of the simplex, then for each I you just check whether this exterior product has the sign that you want, and then you compare all of the products with each other. You iterate through I and do all the products and check the orientation, and then you know whether the simplex is contains that point or not, P0. But this exterior product that you compare when checking whether P0 is contained in the simplex, that's the same exterior products that are used when solving the linear system. And so it turns out that solving the linear system and checking whether the point is contained inside of the simplex, these are fundamentally the same calculation in terms of the exterior products, just applied differently. And in the same way, you can invert the d-adic tensor using the same principles as well. It's a similar principle as before, but just excluding the P0 parameter from the construction. And these simplices, they have a volume, each of them, and that's local information. So if we take a look at this graph, there's also global information or global transformations that we can apply, and that's the red nodes. And so that's where we do a quadrature interpolation, and we take we want to obtain similar information but interpolated along the spaces of these this mesh, instead of just at particular nodes or points where we had the triangle volume specified, which was average on the triangle. So now I have an extendable syntax based on the Grassmann element assembly, where I can extend the solution to partial differential equations and customize it, and I have all of my Grassmann algebra foundations built in, so if I need to do any Grassmann algebra fancy type of things, I can make that part of my solution. Here are some of the examples when we treat the solutions of these partial differential equations as tensor bundles and plot them using the Grassmann element foundational structure, which has been built into the packages that I've been building. Once the potential solution to the equation has been solved, the solution of the partial differential equation can be visualized in a variety of different ways using some of the visualization techniques that are available, and by translating the information and transforming it in a variety of ways, we can plot the results. Part of the goal here was for me to create a computational language and design the interface and a computational language construct for differential geometric algebra, which is able to facilitate the differential geometric algebra seamlessly in engineering type of calculation environment. And that's why I wanted to build this type of engineering calculation from the ground up using the foundations of differential geometric algebra as a basis, and to really just take it apart completely and build it from scratch in a new way using these foundations, but still making it familiar and based on the original, ideas that we're familiar with, but making it a hybrid of that and the unifying differential geometric algebra foundations that I'm talking about in this presentation. And so that's why I go over these mathematical details here, is because it's not just computational language that has to be implemented, but it's mathematical theorems and definitions and axioms that have to be satisfied, that in order to be rigorous about this, in order to be able to seamlessly use this in an engineering environment to calculate with mathematical physics and use differential geometric algebra all in a neat and unifying way, and to have it be convenient, it's necessary to look at the mathematical foundations and the theorems and to think about the proofs a little bit. And that's why I've had this long presentation and took some time to revisit some of these things. So let's review what we talked about so far. It's the foundations of differential geometric algebra. And one of the fundamental themes here was that Grassmann algebra is a unifying mathematical foundations. And part of the goals was to improve the efficiency of multidisciplinary research using mathematics and language. And how do we do this? Well, we use the antisymmetric tensor products from Grassmann and the geometric algebra and the Clifford product and so on. And from that we can derive the rotational algebras and the Lie bivector groups with the exponential function and so on. And we also have conformal geometric algebra with the Minkowski plane, and a mixed symmetry algebra with Leibniz, and there's even automatic differentiation, which is a whole other interesting topic. And we have the Hodge and the Ram and homology with differential and contraction operations, which provides a whole interesting range of topics that introduce other things such as the Betti numbers and the Euler characteristics, which is based on these dimensions of these spaces. And what's particularly important, though, and what everyone might be aware of, is the Dirac and the Clifford product yields the generalized Hodge Laplacian, and that's part of what we covered in the presentation here today, and we used it even as an application in the theorem about the reflection, and then also that leads to the Cartan-Dieudonné theorem about every isometry can be decomposed into at most k reflections, and this particular reflection theorem we proved can be proved in terms of thinking about the Dirac-Clifford product, which is a Dirac operator, and the decomposition of that is the understanding behind that is what helps us understand all of this theory and the foundations of it. And that's why I created Grassmann.jl, because I saw that there were all these different foundations, and looking at it through the foundations of Grassmann algebra and building these foundations using the tensor bundle implementation that I created and the computational language in terms of constructing computational code based on the syntax that the user inputs and deriving from, the type properties to compile code that is optimized for a particular algebra and can, in some cases make a calculation quicker by assuming some sort of subspace or submanifold in the calculation. And what that leads to is the design of the computational language that I ended up with, and I put into my code repository on GitHub, Grassmann.jl, and I've now written a paper about it and included a bunch of the theorems, and some of the information discussed in this presentation is all included in the paper about the foundations of differential geometric algebra, which I conceptually developed alongside programming and developing and researching, designing the computational language for Grassmann.jl. And while I was doing that, I was gathering my thoughts about the foundations of differential geometric algebra, and that's how this presentation came about, and that's how I put all this information together, by writing a paper about it and assembling some slides of information to talk about in the future. So what does all of this mean for the future of mathematics and engineering? Well, of course, the goal with this type of designing of computational language is to improve the efficiency of multidisciplinary research using differential geometric algebra by relying on universal mathematical principles. And that's why I based this presentation on the foundations of differential geometric algebra, and why I went over some theorems and proofs, and why I took a look at some of the definitions, and why I use all this language to talk about these things is because in this particular presentation, I'm not necessarily trying to say that this is how this should all be taught to people, and how the teaching should happen and how the learning should happen. But it is part of how the foundations should be constructed, where how from what to derive, the notation and the understanding that we're going to build, because we need some kind of starting point, some kind of complete understanding. There needs to be a foundational understanding behind all of the other derived understanding so that it all makes sense and is consistent and has a greater meaning behind it. And that's why getting the foundations right is important, and that's why this presentation is trying to organize the foundational principles behind some of these things about the foundations of differential geometric algebra. And if this understanding can be had correctly, then we will be able to transform superficial knowledge into deeper understanding, because we'll have a unified foundations for many different subdisciplines, which is widely applicable to geometry and mathematical physics and engineering as well. So the software tooling will help overcome the present challenges. What are the present challenges? Well, it's not yet standardized or taught in schools and universities, and not yet used for industrial science and engineering unification. And so some of the challenges I've mentioned also, that some of the notation, some of the implicit assumptions made about the interior product, for example, and the complement operation and how the Grassmann laws should be satisfied. Some of those nuances may not have been rigorously thought about by some of the people writing, but I rigorously thought about it when I was programming the computational language design and these foundations I'm talking about here. And it's based on the original Grassmann complement operation and satisfying the original Grassmann algebra laws. And that helps unify things with the differential geometry literature, such as the Hodge and the theorem writings that have been written later on, and things that are based on that. And there's been some modern geometric algebra writings which took a slightly different direction and took implicit assumptions about how inner products work, which somewhat diverges from the original Grassmann. And because of that, there might be some inconsistencies. And I posit that the original Grassmann way is, of course, the correct way of doing it, because that's also how the differential geometry bases some of its assumptions and its theorems. And getting these foundations correct and thinking about correctly matters, because all of the other things that get derived from it downstream have to be consistent as well. So these are some of the present challenges about it not yet being standardized or taught in universities and schools yet, because some of the textbooks and things, they're not necessarily based on this full understanding and may not be consistent with it. And that's why Grassmann.jl, the software, enables ascending future steps. So that's why I created a computational language implementation, and I designed it based on these foundations so that it can be rigorous, and so that it can be used and to help gain a understanding about how the consistent mathematics should be understood, so that there's some kind of access to getting a consistent and correct answer that's consistent with the original Grassmann algebra theorems. And so it's called Grassmann.jl for a reason, because some of the other implementations out there, I haven't tried them all out, but some of the ones I have tried out, they don't necessarily satisfy the original Grassmann laws. But the emphasis in my program is to try to satisfy the original Grassmann laws, and to help from that derive the correct understanding, making sense of things in the world. And that's why I created this Julia package, Grassmann.jl, which is available on GitHub. And I'm also experimenting in the Wolfram language with similar language design principles. They're also based on the foundations of differential geometric algebra. And these fundamental mathematical principles, they're universal. So I could be implementing them in a variety of programming languages. And before I even implemented it in any language, I spent a long time thinking about it and constructing it in my mind. And these things have to be understood before they can be transmitted further, and there has to be a little bit of rigor behind it, and that's why we have taken a look at some of the theorems and so on, and trying to address some of the challenges with miscommunication about how the original Grassmann algebra theorems may not be satisfied by some people's work because they didn't rigorously think about the foundations yet or something. I don't exactly know, but I'm just trying to provide my perspective of how the foundations should be constructed for foundations of differential geometric algebra, and Grassmann.jl is a particular implementation of that in computational language, which manifests these abstract concepts I talked about in computational language. And using that, I verify my thoughts about it. I can use it as a tool to teach myself and to teach other people and to show them, this is how differential geometric algebra works, and it can help me in constructing the computational language and solve a variety of problems. And that's why I created this. Well, why did I release it as open source? Well, the answer to that is this particular project doesn't make much sense if it's not, if you can't check the calculation and verify yourself. Because the foundations of differential geometric algebra, you could be getting confused. You could be getting some concepts confused or something, or mixing some things up, or getting a plus or minus sign incorrect. And that's why having a computational language design, which can be compiled with free software, was part of the goals of the project that I did. And that means that it was an open source license I had to choose, and didn't quite make sense to make it proprietary because I'm trying to get the foundations of differential geometric algebra correct, so that when you derive other theorems and formations from that those things are consistent and make sense. And as a mathematician, I can't accomplish that unless it's some kind of software that other people can download and compile on their computer, and that's why it was free and open source software. And so yeah, that's where the direction I ended up taking with releasing the software, and I have several hundred commits on the repository over several years. And even before I started committing to the repository, I spent a long time constructing it in my mind. And it wasn't just a construction in my mind. I actually programmed it on the computer and went through a whole bunch of iterations of testing and research and development and getting new insights about Grassmann algebra and the foundations and how to correctly implement things, and things that I overlooked and so on. And as things moved along, I ended up with computational language implementation, which has now been refined, and now I have a clear understanding of what the foundations should be and how it can be made consistent and so on with the foundations of differential geometry, and that's what I ended up with. It didn't quite make sense for this thought about differential geometric algebra to be meaningful unless I released it open source, because otherwise it would just be a thought in my head or something I kept to myself, and maybe I could do some experiments with it, but I wouldn't be able to communicate about it clearly with other people. And so it's a component of computational language. I believe that had to be part of the. Well, I just released it out there, and it's out there now, so you can check it out and try it out yourself. And if we end up talking to each other about differential geometric algebra or some kind of calculation, and we get to know each other, and we can talk to each other and use this computational language I designed to do high performance calculations, and to design computational language and functions around the ideas that we're interested in discussing. And that's part. And we don't have to worry so much about all the foundations anymore, because I already thought about all of this. Before even making this presentation and before even writing the first line of code, I had already deeply thought about all of the foundations. And as I implemented them more, I now have the foundations available in the computational language for us to use. And so if there's people who want to participate together with me, you can potentially reach out to me, and we can use Grassmann.jl or something that I'm developing in the Wolfram language to do computations with differential geometric algebra based on these foundations that I've been discussing. So I'm certainly interested in deriving further results and having this be a foundation from which things get built upon further. And that's why I'm a proponent of the foundations of differential geometric algebra here, so that we can have further discussions that build upon it further, and further computational language designs, and further insights that keep building on the science and the mathematics. When I set out to work on this, the tools I desired based on these foundations didn't exist. So I went ahead and created the kind of foundations I envisioned. Please help sponsor and fund this research and development project. There is a need for funding of mathematical research project outside of academia.